Let's begin with integration. For a function f, whose graph is shown here, the integral of f from a to b is just the area under the graph of the function, as depicted there in the blue region. If f is a continuous function, then the area is well defined, and it's the common limit of various upper and lower sums, which you've learned about in calculus. The integral is denoted by the integral sign, and then the limits of integration a to b, and then f, depending on an independent variable x, and integrated across x, f of x dx. One of the main things we learn in calculus is something that relates the integral and the derivative. If a function g is an antiderivative of f, in other words, its derivative, g prime, equals f at all x, then the fundamental theorem of calculus tells us that the integral of f can be computed by evaluating g at the limits of integration. The integral from a to b of f is g of b minus g of a. And we spend a lot of time in our introductory calculus classes learning how to find antiderivatives of functions. But finding antiderivatives can be hard. In many cases of engineering and scientific and economics interest, the functions do not have known antiderivatives. So the integral must be approximated by a finite number of function evaluations. In other words, evaluating f at particular values of x. Carrying that out is what the next few units in this module are about. Another issue that impacts our ability to accurately determine the integral is that the function f may not be completely known. Perhaps only a finite set of x, f of x pairs are known. For instance, f of x1, f of x2, up to f of xn, where x1 is a and xn is b, and the intermediate points are spaced in between a and b. But the scenario is that the integral must be estimated from these values alone. So how can we do that? Additionally, sometimes the evaluation values may be known to likely have some errors, so that the evaluated value of f at xi is the true value f of xi plus mu I, where mu I is some form of an evaluation error. In an engineering application, there might be a sensor which is measuring a certain physical variable, but the sensor itself is subjected to interference and electrical noise and calibration errors and so on, and therefore the sensed value is not exactly equal to the true value of the physical variable that it's observing. It's clear that these type of errors will further complicate the estimation of the integral, and we'll have a small discussion regarding those.